Yeah, sorry, it's not working again. I have reported it, but yeah, there's room next door though, okay? Okay, so what we're going to finish off today is finish off the partial fractions stuff and then do the last integration strategy, which is integration by parts. So this week we basically started with probably the most powerful technique we've got, which is integration by inverse trig substitution, because it's designed to get rid of problematic square roots. The next method we did was a weird one, right? So I showed this one mainly to show you that the integral formulas for sec and cosec that are on the formula sheet, this is where they come from. And this is a weird one. I wanted to illustrate this to show that sometimes you have to be quite creative when you're doing integrals. Certainly not something I expect you to be able to come up with your own methods yet. It's a skill that comes with integration skill is one that comes with lots and lots and lots of practice, basically. All right. So this one, I covered it to show you where these two formulas come from. Now let's forget about it. We're not going to do this one. Right? This half angle one, we're not going to do. I mean, there is some questions in the practical classes for the practical class sheet next week. There will be some questions on it, but I'm never going to ask it in tests or an exam, okay? The next one we did was how we integrate rational functions. So provided the order of rational functions ratio of polynomials, provided the order of the polynomial up the top is less than the order of the polynomial, you can break it up into separate pieces as long as you follow the rules. It's very much like common denominator backwards. That's exactly what you're doing, right? And the way we do it is we follow a couple of rules, which basically distinct linear factors spit out fraction parts with the linear factor on the bottom and an unknown constant up the top that you have to find. Repeated linear factors spit out terms where the powers march up. So if this is, say, cubed, it would spit out 3 terms, right? One with an x minus a to the 1, and one with an x minus a to the 2, and a 1 with an x minus a to the cubed, each with a constant up the top. The next case is if you've got a quadratic that you can't, that's irreducible, so it has no real factors or real roots, whatever you want to call it, that will spit out a term with an unknown linear function up the top. And you notice the pattern. A linear gives an unknown constant. It's a polynomial 1 order less. A quadratic gives an unknown linear, and this pattern continues. If you had a cubic on the bottom that you couldn't factor, that would spit out an unknown quadratic up the top. The problem with those ones is, one, the algebra starts to get rather tedious, and 2, integrating things with cubics on the bottom is not pleasant, right? And that will usually involve functions you haven't heard of, so we're not going to do them, right? That's why we stop here, right? To find the constants, you basically do common denominator again and put everything back together. Remember, if you follow the rules, the constants must exist and must be unique. If you get gibberish answers, it means you're doing something wrong. You're not following the rules properly, or something's wrong. It's guaranteed to work. Okay? And the other thing, last thing to note is, especially when you have irreducible quadratics, you will often get a term, usually you'll get 2 terms. You'll get, say you had a quadratic on the bottom that was x squared plus 1. That doesn't have any real roots. That'll spit out 2 terms. There's a constant times x on x squared plus 1. That's a simple substitution because the top's the derivative of the bottom, so it's going to become a log. And you'll get a constant over x squared plus 1. And that one is straight off the formula sheet, right? One of the integrals on the formula sheet is this one. Right, we proved a few weeks ago that the derivative of inverse tan was 1 over 1 plus x squared, or 1 over x squared plus 1. Order makes no freaking difference. That means that the integral of 1 over 1 plus x squared is inverse tan plus c. Right? Remember, as I said, that the last page of the formula sheet actually has a lot more information on it than you realise when you're trying to do integrals. Now, there's a couple of examples. Now, I want to... Where are we? Right, we see this one, for example, has 2 linear factors, right? So it's already factored for you too, which is nice. So the rules of partial fractions say that each of those will spit out a fraction with the same linear factor on the bottom and unknown constants up the top, which we have to find. Now, if you give this a common denominator, then you've got the bottoms are the same, so the tops have to be the same. This is not an equation to solve for x. This is an equation that must be true for every single value of x, right? So it's an equation in a and b, right? The constants you're looking for. It's not an equation in x. The fastest way to get the constants is to pick convenient values. And when you've got linear factors, it's easy. So, for example, if you substitute x equals minus 1/2 into both sides, now granted there's no x over here, that doesn't matter, that'll annihilate that term and give you a. Right? And then when x equals 2, that'll annihilate that term and give you b. Right? Now this is one I did by hand. So here you've got an irreducible quadratic, so the linear bit spits out an a on x minus 1, and the irreducible quadratic bit spits out a bx plus c, so we've got to find bx and c. B and c, sorry. Now when you give this a common denominator, again, this is an equation that's true for all x. Now, if you look at it carefully, you see, well, if I plug in x equals 1, I'm going to get a straight away. So then you know what a is. If I plug in x equals 0, I'm going to get c nice and quick, right? So then you know a and c. You've only got one left. Pick any value of x you like. Pick 2 to make sure you get the same answer. Okay? Now the last one we have to do is one with a repeated linear factor. These are actually the worst ones. Right? And I'm going to do the partial fraction decomposition of this by hand to show you why I think these are the worst ones. Right, so this one we've got to, let's not worry about the integral for now. Basically we've got x squared plus 2x all over right, so we can see that the order of the polynomial on the top is 2, the order of the polynomial on the bottom is 3 if I expanded it out, so we can go straight to the rules. And the rules say if you have a repeated linear factor, it'll spit out terms where the power of the linear factor basically marches up. All right? So if it was, say, x plus 1 to the 24, you'd have 24 terms. I ain't going to do that. All right? 3 is probably the limit. All right? But notice the pattern. Now, if I give all of this a common denominator, so the first one I have to multiply top and bottom by x plus 1 all squared. The second one I just multiply top and bottom by x plus 1, and see the third one I don't have to do anything. All right, so you give it a common denominator. All right, so now the denominators are the same, so what you must have is for all x, you must have this equals. Now these are the worst ones because there's only going to be one useful value of x, isn't there? If I plug in x equals minus 1, I'll get c, but there's no quick way to get a and b, is there? Right? There's no other values to pick. Right? So here it's up to you. You do it whichever way you want. Right? And so in the class examples, which I'll do in a sec, I've equate coefficients. Let me show you a different way. Well, when x equals minus 1, I'm going to get one of them. Yeah. All right, so I've got c now. All right, that's fine. All right, so I've basically now got this down to the problem now is, of course, I'm out of values. Right? There's no quick way to get a and b. But remember, this is an equation that has to be true for all x. So you've got two equations, you've got two unknowns, you need two equations. So one way you could do it is plug in two other values. Right? To make life easy, don't pick x equals 43 or some bollocks like that. Make it easy. Right? We've used minus 1, let's use 0 and 1. Right? Make life simple. Now when x equals 0, you get that. And say when x equals 1, you get right, two equations and two unknowns. Right, that you could do. Those of you who are doing 101.2, if you want to use linear algebra and matrices and row reduction and all of that, knock yourself out. Right, I don't mind. Okay? But these are relatively simple to solve. So what's the first one basically says, if I plug that in the second one, right, done. Right, and if you want to check, you could plug in another value, but that's how we've got A, B, and C. Right? So these ones are the worst because the convenient value of x won't be there. Right? If you don't want to do it this way, that's fine. What you could do instead is you could equate coefficients. They're all equivalent. How you solve it is totally up to you. As long as what you do is logical and correct, it's going to work. Remember, the constants are unique and they're guaranteed to exist. So it shouldn't matter how you find them as long as you frickin' find them. Now what I did here instead is I just expanded this out and wrote it as a, something times x squared plus something times x plus something, which has to equal x squared plus 2x. So if you've got two polynomials that are equal, the coefficients have to be equal. So this is basically telling you that a has to be 1 2a plus b has to equal 2, and a plus b plus c has to equal 0. Now the advantage of this method is that although technically it looks like 3 equations in 3 unknowns, right, they tumble out. The first one, obviously, you get A, done. The second one, you get B, done. Third one, right? But you can use matrices and stuff if you're doing 1012 if you wish, right? Again, I've got the, obviously, well, hopefully I got the same answer I got before. I found C is -1, A is 1 and B is 0. Oh, thank God. All right, done. Doesn't matter that one of them's 0, right? I mean, if you're really worried and you want to check your answer, what you've shown is this equals this. Give this a common denominator and make sure you get back to here. Right? So to give this a common denominator, I'd have to multiply this. This would be x plus 1 all squared. That's x squared plus 2x plus 1 minus 1. Don't do it in your head though. Right? But, right? Once you've got it, these you can integrate. These are, so this one's a simple, if you let, you know, if you need to do the change of variable, do it. If you let u equal x minus 1, then basically du equals dx. So this is essentially the integral of 1 on u minus u to the minus 3. Right? Easy. Right? The integral of 1 on u is log of u. The integral of minus u to the minus 3 is minus a half u to the minus 2. Right? Then plus, obviously, as always, the plus c. Right? And then you're done. Right? So they're the, you know, there's different methods depending on the question. The way I always try and make life easy. Right? So if you've got linear factors, pick convenient values of x. If it's quadratic, you should have two convenient, one or at least, you should be able to find at least two of the constants by picking convenient values of x. The ones with repeated linear factors, they're the worst. Right? And do it whichever way you're comfortable with. If you want to equate coefficient, you know, doesn't matter. Pick a method you like and do it. Right? As long as it's right, it's fine. You know, as long as you're not doing anything naughty, I'm happy. Huh? Okay. Right, and that's how, and as I explained, the pattern does continue, right? But you know, if we go to say cubics on the bottom, you can do the partial fraction decomposition, but the integral starts to get a little bit hairy, right? And a lot of the time it will involve functions you've never heard of. So as I showed you before, this is the problem with integral. You know, you remember that? I love that comic. Let me show that again. Well, I only. What? Oh, whatever. All right. I love this one. All right? Because this is what, you know, it basically summarises everything that can almost go wrong. Yeah, I love this bit because this happens all the time. What the heck is a Bessel function? I love that one, right? But, you know, cubics and stuff, if I ask you to integrate sorry, hang on, let me increase so you can actually see it. Right, if I ask you to integrate that, I mean, that's actually straight off the formula sheet. Remember, arctan, the same thing as tan, inverse tan. Right, but if I make that a cubed, right, you could do that one. Now, the middle term, you could though. I wouldn't give it to you, but you could. You know? Right, and it just, slight change in the power, it just gets worse and worse. Well, that was not too bad. Well, that actually looks nice. Let's be stupid. Right? That one can't be done. Right? What that output means, it can't do it. Right? It's the root of an order 66 polynomial. Right? So, yeah, we stop at, yes? I think that means you can technically do it, but it have to be approximate. You have to. Oh, okay, well, give it a go. You want to solve an order. If I hit, actually, I'll show you. It means it can be done. right? But notice also it's complex, right? Remember I said that there are lots of integrals that are easier to do in the complex plane, which we can't do yet, of course, because you haven't done complex function theory, right? But the key is the pattern of partial fractions does continue. The reason we stop at quadratics, I mean, the other one is, what have we got? If I've got, say, what's the one we just did, x? Right, that's basically one we just did. And of course this power can get higher, but there's a limit to how much you want to do this by hand. Oh, well, that's not too bad actually. Actually, let's make this a bit more, just to show slight change. Oh no, because that's x plus 1 all squared. Is that right? Is that right? Oh, that's interesting. Right, let's, whatever, right? But obviously I'm not going to get that silly about it. This will actually have 37 terms. It just turns out 34 of them are 0, right? You don't want to show that, right? So I'm not going to be silly about it, okay? And we're going to stop at irreducible quadratics, right? But the pattern does continue, but the integrals will get a little bit nasty. That's the problem. Okay. Right, now there's one more. So all of these, we've now done, well, partial fractions isn't really an integration by substitution method. It's a very specific method for rational functions. We're basically done, we've basically done all the possible substitute. Now there are a couple of others. So we've done integration by inverse trig substitution. Who's ever heard of hyperbolic functions? Anyone ever heard of? Right, they're sinth, cosine, tanth. They're very similar in behaviour anyway to the trig function. You can use, there's integration strategies involving the inverses of those too, but they're not very pleasant. And I always think they're not worth doing because the hyperbolic functions can be written in terms of exponential functions. When you're integrating exponential functions is always awesome, right? Because exponential functions are the easiest thing to differentiate and integrate because you just get e to the x. You just keep getting it back. So I never bother with them. If I've got one involving hyperbolics, I just use exponentials. So, that's why I don't really talk about it too much. But that's basically it for the substitution methods. There's other, much more advanced methods than what we've covered. One is using complex functions. That's very, very, very powerful, but you wouldn't do that for a few years. You have to do complex functions first. And there's other ones, things like differentiating under the integral sign, sometimes actually adding a constant in there or adding a fake variable in there will let you work some integrals out. I mean, I've got this book that basically when I was a postdoc, my postdoc supervisor found this book somewhere, and the book was called Irresistible Integrals. You have to be a mathematician to go, ooh, that looks interesting. All right? But some of the integration strategies in that book are absolutely amazing, but so out of left field. That's the whole problem with integration. It's a very tricky business, integration. Right? So we do the techniques we know work, and what you hope is that if you keep going in maths and these techniques will build your skill and you attack harder ones that you do much later on. But anyway, the last technique we're going to do is integration by parts. Now, some of you have probably done integration by parts before. Right, so integration by parts is like the integral version of the product rule, and that's actually where it comes from. But I teach this last. Most textbooks will teach this much earlier than I have. Now, the reason I teach this last is you do this one last. Always try substitutions first. When you get the hang of it, you'll be able to look at an integral and work out what's the best way to go. If it's a rational function, obviously partial fractions. Right? Anything else, you try substitutions first. When you build up your skill, you should be able to do them in your head and work out quickly, is a substitution going to work or not? If it doesn't, because this is the last step, right? This is it. This is the last one we're going to do, right? And so integration by parts is where we have a product of functions, where we have to integrate a product of functions, and then a substitution's not working, right? And whatever you do, do not do this. Because that is never, ever, 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 ever true, right? That don't work, okay? And you wouldn't believe how often we see that, right? And it's so wrong, it's just not even funny anymore. It's a bit funny, but not that funny, right? So this one we use to handle products. Now, basically, if I go back to the product rule for differentiation, of course, remembering integration is the opposite of differentiation. We've got the derivative of u times v, we know is v to u dx plus u to v dx, or whichever other way around if that's the way it doesn't matter. Now if I integrate both sides, so whatever I do to the left I'm allowed to do to the right, if I integrate the left I get just u times v, right, because the integral undoes the derivative, doesn't it? Right, now integrate the two things on the right, they're sums, so I'm allowed to do each integral separately. And just like with the chain rule, if I think of the dx's as fractions, that basically simplifies out to uv equals the integral of v du plus the integral of u dv, right? And we usually rearrange it in this form, right? So we remember the formula by the integral of u to v is uv minus the integral of v du, right? And it's one of those things that I actually have another comic on my door that says integration by parts. Well, that looks easier, off you go. I haven't explained how to do it yet, of course, right? But this is called the integration by parts formula. It's on the formula sheet if you don't remember. The way we work with this is, we have an integral that's a product of functions that, so say it's like what I've written here actually, right? Say we've got a product of functions. So you can imagine there's a bit that I could call f and a bit that I could call g dx, right? So the way we use this thing is we let one part equal u and one part equal dv, which includes the dx bit, right? The hard part is, of course, choosing them in such a way that it'll work, right? Now, to apply we first factor the integrand into two bits, a bit that we call u and a bit that we call dv, which equals something times dx, right? And remember that something could be 1, right? When you ask, the classic one is, I haven't proved to you yet the integration formula for log of x, right? So the integral of log of x is x log x minus x plus c. Right, the way we prove that is with parts, but then you might think, well, hang on, log of x is on its own. Technically, it's 1 times log of x, right? And you can make the integration by parts formula work, right? So remember, choosing a bit to equal 1 is perfectly valid, provided it works, right? Then we work out an expression for du by differentiating u and using like the fraction trick like we do with the chain rule, moving things around. And we integrate the v by integrating the dv bit, right? And we choose these parts in terms of these principles, not rules. The integral of v we can do somehow, right? That's a big if. And that the new integral you get on the right, so you start with an integral, this process is going to spit out another integral. And the hope is that one's doable, right? This is also kind of like L'Hopital's rule. You might have to apply integration by parts several times, but I'm not going to be stupid about it. 2, maybe 3 times if I'm being cruel is it. Right? If you're working on an integral problem and you're on your 7th application of integration by parts, you are not doing it as I intended you to do it. Right? I'm not going to be that stupid about it. I'm not going to be, unless I stuff up, of course, right, and give you a really difficult one. Right? Now, in general, we choose the u and dv to be the most complicated factor that can be integrated. And for years, I've been using this table as a guide right? Now, it rarely doesn't work, right? But it is a guide, not a rule. What this table was telling you what to do, right? If you've got a polynomial times an exponential, or a polynomial times a trig, and a simple substitution is not working, let u equal the polynomial bit, dv be the exponential or the trig bit, and integration by parts should work. If, on the other hand, you have a polynomial times a log, or a polynomial times an inverse trig, and a simple substitution is not working, you would let u equal the log or the inverse trig bit, dv equal the polynomial bit, and parts should work. Right? There's another way people memorise this is there's this word ilate, right? And so this tells you if you have because you've got to pick u and dv, right? This is telling you A is for algebraic, another word for polynomial. I think because ILPTE isn't a word. All right? This tells you if you're algebraic times a log or an algebraic times an inverse trig, let u equal these two, dv equal the A. Whereas you've got a polynomial times a trig or a polynomial times an exponential, let u equal the A, dv be the trig or the... It's the same thing as the table, basically. Right? And it's not a hard and fast rule, but it will work most of the time. The only time it doesn't work is with really nasty ones. Right? But I've been using this table for years. It was funny where I got it from, actually. When I was in year 12, I did high school in New South Wales, and at the time, this was 1995, not that long ago, not that old. Right, but it was 1995, and in New South Wales at the time, the highest level of maths we had was called 4-unit maths. It was very hard, right? Very, very, very hard. Very few people did it. I think in WA, about 20% of Year 12 do maths specialists, yeah? I think it's about 20%, isn't it? Right?
Not high school.
But it's statewide. So in New South Wales, guess what was the percentage that did the highest level of maths in New South Wales when I went through? It was less than 5%. Right? Very few people attempted it. It was obviously I was good at maths. I liked it. But anyway, somebody in their infinite wisdom decided, oh, this is too hard. We're going to provide a formula sheet. Right? And I'm a big fan of formula sheets. It's awesome. They released this formula sheet that's full of so many errors it would boggle the mind. A monkey must have wrote it. Right? It was just full of typos. Things were wrong, but there was one gem, and that was this table. And I've used it ever since. This is the only thing on there that was useful. So that's where I got it from. Anyway, let me show you how it works by looking at proving the integration formula for log of x. Right? Now, technically, this is a polynomial times a log, because it's one, you can think of it as being 1 times log of x. Right? Now, this table tells me I let u be the log bit and dv be the polynomial bit. So in other words, I'm going to let u equal log of x, and I'm going to let dv equal 1 times dx. Right, so the dv includes the dx bit. Yes?
So with the table there, because I see like the ilate thing tells you the order, it doesn't have like inverse trig and then 1b dv.
Right.
Is that because you use something else?
No. Thank you, I forgot to explain that. If you have an exponential times a trig, this table's telling you it makes no difference which part you let equal u in dv. If you have a log times an inverse trig, it makes no difference. Now, exponentials times logs or trigs times inverse trigs can't do. Right? Those ones are really hard. Right? So, let's actually try one. What if you had, say, what would that be? That involves a function you don't know. Right? So EI is a function called the exponential integral. Right? You don't know it. And if you had I don't think this one is even doable. No. So when Maple spits out the integral again, it's because it's given up. I can't do it. right? So those ones we're not going to do, okay? Anyway, let's go back to this one. So you break it into pieces. So I let u equal log of x dv equal 1 dx. Now I differentiate the u equals log of x, that gives me du on dx equals 1 on x. So du equals 1 on x dx, yeah? Dv equals 1, if I integrate both sides I get v equals x. Technically, v equals x plus c, but I don't worry about that constant. I just slap on a constant at the end, that'll take care of it all, right? You only need one integration constant, right? So I've got u, dv, now I've got du and v. My integration by parts formula says that the integral of u dv equals uv minus the integral of v du, right? So u dv equals uv times the integral of v du, and the hope is this is doable. Right, which it is in this case, okay? And this is how you prove the integration formulas for inverse sine, inverse cos and inverse tan that are on the formula sheet as well, because they're like polynomials times inverse trigs. They're 1 times the inverse, and you can do those exactly the same way as this one. So now I've proved all of the integration formulas on the formula sheet. Right? Now there's a couple of more examples in here. Now, which one do I want to do by... I want to do this one by hand. Right, let's have a look at, say, this one. Now, you should note that no substitution is going to work, is it? There's no, like letting u equal x squared, that's not going to help. You're going to end up with the integral of u e to the root u. That ain't helping, right? Nothing else is going to help, right? So it should be obvious at this stage now, no substitution is going to work. It's a product of functions integration by parts, right? I have a polynomial times an exponential. So the table tells me I let u equal the polynomial bit. Right, so now notice in my head, I've written the integral as the integral of u dv. Yeah? I know the formula tells me that the integral of u dv, so I need u, I need v, and I need du. Now if I differentiate this, that's easy. And just like we do with integration by substitution or the chain rule, that's just 2x. Du is therefore 2x dx. Yeah? This one, if I integrate both sides, I'm basically saying v is the integral of e to the x. So I could add a plus c here, right, which I'd have to bring along. What you'll find is it'll just add to the one at the end, so don't bother. Right, just add a plus, just whack in a plus c at the end, that'll take care of it all. So now I can therefore say is u times v, so u is x squared, I found now v is e to the x, minus the integral of v du. All right, I just plug everything in. Clean it up. As always, I take constants outside. I get to here. Crap. I can't do that one either. But that one is easier than what I started with, right? And I could use integration by parts on that one and go again. Right? So sometimes you'll have to do it twice, maybe 3 times, that's it. Right? Let's now attack this bit. I've got another polynomial times an exponential. Equals uv minus the integral of v du. Clean it up. Aha. I can do that one. Right? Technically it's plus c, but I haven't finished the problem yet. I'll whack the c on at the end. That's fine. Right? So now I just plug this into here. So therefore the integral of x squared is, now when you get to this step, just be careful of the signs and everything. And I just add now a plus c now, right? And just clean this up. Don't, worry about expanding and collecting like terms is all I'm looking for, right? Don't factor, unless I've asked you, don't factor out the x or, factor some of the x's. I mean, technically you could clean this up a little bit, but I don't care, right? Right, but as I say, the thing is, sometimes you'll have to apply integration by parts a couple of times, twice, maybe 3 times is it. Now you could imagine that in this one, what you see what's happening is every time you apply it, you're dropping the power of x out the front of the exponential, aren't you? Right? So until you get x to the 0, that's right. That gives you something you can integrate. So yes, you could keep going with this. So I could ask you, well, what is the integral of x to the cubed? Right? That will require 3 integration by parts. Oh, yes, of course, thank you. Right? That would require 3 integration by parts. Yeah? That's about the limit I'd give you. Right? That will require 37 integration by parts. I'm not going to get you to do that. Right? So 2 or 3, maybe 3 if I'm being cruel, should be it. If you've got a problem that's requiring more, then you're doing something wrong. Most likely what you're doing wrong, if it's an integration by parts question, is you've picked your u and dv the wrong way around. And what you're doing is you're making the integral that spits out on the right, this bit, harder than the one you started with. That shouldn't happen. It should be at least it should be easier or at most as hard. The actual worst ones to do, and this will be in the practical sheets next week, is the integral of exponentials times trigs, right? Because they're a little bit tricky, right? Because what will happen with those, so if I asked you what is the integral, what's this one? Well, you see no substitution's going to work, right? So, and of course my integration by parts tables tell them, well, that doesn't tell me what to do with an exponential time. It's what it's telling you is because they're in the same part of the table, it makes no difference. So for the hell of it, let's let right? Now if I go through the process, integral of sine is minus cos. Let's call this I. There's a reason I'm doing that. Is u times v minus the integral now it's not harder, but it's not easier either, is it? Right? But, all right, so I apply integration by parts again. And what will happen then is you'll find that you'll get that. I'm going around in circles. I apply integration by parts again. I'm not getting anywhere. Yes, you are, if you think about it. That's what I'm looking for. So I've basically got I equals All right. So this one I still only require 2, but if you missed it, you would just keep going and going and going. As I said, 3 is the limit. Right? If you're not getting anywhere after 3 applications of integration by parts, something's up. Okay? Anyway, there's some extra examples there. Now, for all we're going to do more or less for the remainder of the unit is integration. Right? Everything we're going to be doing involves integration. So being able to handle all these different integration strategies is really crucial. Right? So please make sure you do put the effort in, go through all of these methods except the half angle one. You can give that one a miss. Right? But all of the rest, right, we're going to need your skill in that as we go on. So make sure you do work through the class examples and everything, because it will really help for everything else we're going to do for the rest of the unit. All right, but I'll leave it there for today. All right, I'll see everyone next week.